Okay, in this video I want to introduce you all to 3 different formulas, one of which you probably saw before in Cal 1, and these are all formulas to help us do numerical integration. So there are many different integrals that we cannot integrate by hand. We do not know the antiderivative of every possible function, and so we might want a way to still evaluate an integral, a definite integral, and the way to do that is to use some of these numerical techniques. So there are some ways to approximate how much area is under a curve. And if you recall, that's actually how we originally started defining integrals when we talked about Riemann sums last semester in Cal 1. You should have learned, or whenever you took Cal 1, you should have learned about the fact that you have a curve, and we would do these sort of rectangles. So you might break your underneath the curve maybe into 3 sections, and you would draw this rectangle, and you might draw this rectangle, and you might draw this rectangle. And you would add those areas up, and that would give you an approximation for the area under the curve. And that would be like I think those were like the right Riemann sum, so it was like Rn maybe, depending on the notation that you used. And then you could also do them from the left endpoint of each point of your interval. You could draw a rectangle for each of those, and then maybe this one, and then you would add up these, and you would have 2 different approximations for the area under the curve. So you could have left endpoints or right endpoints. And in this case, we used like here n was equal to 3, we had 3 rectangles, and you could change the number of rectangles. And we talked about the fact that would be an approximation of the area under the curve. And from that, we learned about what an integral was, and that's how we ended up defining an integral, was that it was an infinite sum sort of these rectangles. So now we're going to do some generalizations of that. Instead of going left endpoint, right endpoint, we're going to try to talk about some techniques that will maybe approximate the area a little bit better, because as you can see here, these are sometimes underestimates and sometimes quite big overestimates. So we want some better techniques to find the area under this curve and approximate it the best way that we can. So the first technique we're going to look at is known as the midpoint rule, and this one may look familiar because depending on what you covered in your Cal 1 class, a lot of people do the midpoint rule as another way to talk about Riemann sums. And so in this one we take an integral that we're going to approximate from a to b, and we're going to take f of c1 plus c2 all the way up to cn for n rectangles, and add those up, it's missing a parentheses there, and multiply by the width of each rectangle, so the delta x. So delta x is your b minus a over n. Cj is the midpoint of each interval that you create. And then they have a way to calculate that here. This is the formula of how to calculate that midpoint. Generally, you can calculate it by hand, or it's pretty obvious. If you have an interval from 0 to 1, obviously the midpoint is 0.5, so that's not hard. So here, for example, we'll draw this out so you can kind of see what it looks like visually. So we have some curve, and maybe we have we're going to break it into 3 pieces. And so what we would do is find the midpoint of each interval, which is here, and we would use that as our height for that rectangle. Similarly, here might be our midpoint, so we would come here and draw this one, and this might be our midpoint here, and so we would use this height and draw this one. So this would be a way to approximate the area under this curve using midpoints. So this would be like f of c3, and this would be f of c2, and this would be f of c1. And we would add up all of those values multiplied by the delta x business in order to get the area of these 3 rectangles added together. So that's kind of the idea of the midpoint rule. It's taking the middle function value and using that as the height of your rectangle. So the second rule we're going to use is the trapezoidal rule. And instead of using rectangles, the idea of this formula or approximation is to use trapezoids. So trapezoids start to maybe approximate the curve a little bit better in terms of not having those sort of sharp rectangular lines. And so here you'll see Tn is 1/2 delta x, and then you get these sort of y0 plus 2y1 plus 2yn minus 1 plus yn. And that's really coming from thinking about adding up the area of a whole bunch of trapezoids. So let's try to draw the picture of this so you can kind of see where that's coming from. So again, let's say we have some curve, and we're going to split this into sort of 3 pieces. Okay, and then the first one, we're going to take the trapezoid, we're going to take y0 here, and then we're going to take y1 as our other base of our trapezoid, and then we're going to draw a straight line across. So we're going to use a straight line at the bottom, the diagonal sort of line between these points at the top, and that's our first trapezoid. And then we're going to draw another trapezoid using this as our first base, and then the end point of the height of the second end point as our second base. Draw the diagonal line, we get our second trapezoid. And then finally we use this guy, we draw here, and we get a third trapezoid. So you can see if we start adding these areas up, this is a much better approximation of this curve, because these sort of linear lines are really much closer than a straight line all the way across. And so you should notice that we only use the far left height once, so you'll see that once in this equation, and we use the far right height only once, and then all the heights in the middle we use twice because they're the base of two trapezoids, right? So this is the base of this trapezoid as well as the base of this trapezoid. And it's really just coming from, if you remember, the area of a trapezoid is 1/2 your sort of base, and then times height 1 plus height 2. So that's where that's coming from. And it's really just using the area of a trapezoid idea to get all these different trapezoids added together. And then one thing to note, if you're sort of paying attention, you want to see relationships, is that the trapezoidal rule, TN, is actually just 1/2 of your right endpoints plus your left endpoints. So you could probably look that up. If you actually added those together, you would get the same formulas as what you get here. So that's the trapezoidal rule. Definitely a better approximation than just using the midpoints, but a little bit more complicated in terms of having to evaluate a few more things. The final rule I want to talk about in this video, and then we'll be able to use those moving forward, is to talk about Simpson's rule. And Simpson's rule here is one that's even a better approximation generally in terms of what they're using to calculate the area under the curve. So first of all, we can only use this for even n, so that's something that's kind of important. And we're going to talk about delta x, again, just like we had before, b minus a over n, so the sort of width across. And the y values, the yj's, are going to be f of a plus j delta x. And then the nth approximation for Simpson's rule is given by this lovely formula here, 1/3 delta x, and then we have all these sort of values added together. And so this one is not as intuitive geometrically as some of the others, because what shapes we're actually using here, we might have a curve like this, and then we start sort of splitting this into pieces. We're actually sort of taking 3 points, so maybe this point, and this point, and creating sort of the parabola that you create by doing that. And then we might take this point, and this point, and create the parabola for that one. And then we take this point, and this point, and that parabola might be more curved upward. And what we're doing is finding the area underneath those parabolas. So we're kind of taking the area under here, and then we're going to take sort of the area under each of these parabolas, and it's not drawing very well on here. But we're taking those areas and adding them up. So it's kind of helping with that curve, right, to keep the curves of our lines. So we're just taking the areas under those parabolas and adding them up, and that's kind of where these numbers are coming from. So again, you really only use the far endpoints once. It's a little bit harder to see this alternating business here, but you can follow along in the book if you want. I think the book has a sort of demonstration of how these things end up working out. But you use sort of every other point more times than you use the sort of points that are at an even value. And that's also why we need an even n, right? Because we have to do this alternating business, 4, 2, 4, 2, 4, 2, 4, 2, ending with a 4. So if your n isn't even, then it won't work out that way. So these are your 3 equations that you're going to use to do different approximations of area under curves. And we will practice them in class next time, so be prepared to do that.